In the second part of Precalculus Lesson 10, we work on finding complex zeros of polynomials. This lesson comes from section 2.5 in the college algebra textbook, and we get started by finding all zeros of the polynomial f of x equals x cubed minus x squared plus 4x minus 4. And we additionally factor this polynomial to linear and irreducible quadratic factors. We start by applying the rational zeros theorem here to find potential rational zeros of plus or minus 1, plus or minus 2, and plus or minus 4. And then, as always, I like to start with x equals 1 to determine if that's a 0. I divide x minus 1 into 1 times x cubed minus 1 times x squared plus 4x minus 4. Bring down the 1. And the next step in synthetic division, we get 0, 4, and we have a remainder of 0. So indeed, x equals 1 is a 0 here. Additionally, it allows us to factor f of x into x minus 1 times 1 times x squared plus 0 times x plus 4. At this point, we have factored this polynomial down to linear and irreducible quadratic factors. X minus 1 is a linear factor. X squared plus 4 is an irreducible quadratic factor since we cannot further factor it over the real numbers. And one additional thing we need to do here is to find the complex zeros. So if we look at x squared plus 4, set x squared plus 4 equal to 0, we will be able to identify complex zeros here as well. So x squared plus 4 equals 0. From that we get x squared equals negative 4. X would then equal plus or minus the square root of negative 4 or plus or minus square root of 4i. We find x then equals square root of, x equals either 2i or negative 2i. And we have 3 zeros, 1 real, 2 not real. Now, to factor f of x over the complex numbers, we note these zeros that we found of 1, 2i, and negative 2i. We can factor over the complex numbers by simply writing f of x as x minus, remember, if 1 is a 0, x minus 1 is a factor. If 2i is a 0, x minus 2i is a factor. If negative 2i is a 0, x minus negative 2i is a factor. So we have f of x equals x minus 1 times x minus 2i times x plus 2i. And we have factored over the complex numbers. The fundamental theorem of algebra and complex factorization tells us that for a polynomial function f with degree n, where n is greater than or equal to 1, then f has at least one complex zero. In fact, f has exactly n zeros if we count multiplicities. So some examples here. I have f of x equals x cubed minus x squared plus 4x minus 4. We found the zeros here already were x equals 1, x equals 2i, and x equals negative 2i. So note that indeed, with this degree of 3, there are 3 zeros, 1 real and 2 not real zeros. For g of x, to find the zeros here, if we set g of x equal to 0, we have x plus 2 squared equals 0. So we have 1 0 of x equals negative 2, but note that that 0 has a multiplicity of 2, and so if we're counting multiplicities, we count x equals negative 2 as being a 0 2 times, so we do have 2 zeros here. Now, find all zeros of f of x equals 3x to the 4th minus 22x cubed plus 55x squared minus 46x plus 10. As always, we start by finding possible rational zeros of plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10, plus or minus 1/3, plus or minus 2/3, plus or minus 5/3, plus or minus 10/3. We will use Descartes' rule of signs to help us out here. It's certainly not required to use Descartes' rule of signs, and you can skip that if you like. But in this case, we'll find that it helps to eliminate some of these possible rational zeros. If we look for the number of positive real zeros, we look at f of x going from left to right. We have 1, 2, 3, 4 sign changes. So there will be either 4 or 2 or 0 positive real zeros. The number of negative real zeros we get from f of negative x. And if you see, I have f of negative x here. There are no sign changes, so there will be 0 negative real zeros. Now, to find all zeros of this polynomial, we have the possible rational zeros. We now don't need to look at the negatives here because we know there are no negative real zeros. And so instead, I'm going to use the remainder theorem here to remember if I plug in 1 into f of x, I find f of 1. I find that in this case, f of 1 is going to equal 0, which tells me that indeed x equals 1 is a 0. Okay, so we have a remainder of 0 when we divide f of x by x minus 1. What about 2? So f of 2 here would actually be equal to 10. Whoops. Sorry, getting sloppy there. And I worked these out ahead of time because this would take a while. So 2 is not a 0 because dividing by x minus 2 would give us a remainder of 10. What about 5? F of 5 is equal to 280, not the 0 that we're looking for. So 5 is not a 0 here. What about 10? F of 10 is equal to a huge number, 13,050. So again, x equals 10 is not a 0. We move on to 1/3. F of 1/3 does equal 0. And so 1/3 is a 0. And I think having 2 zeros, we can move on from here. So to find all the zeros, we have the rational zeros of 1 and 1/3 so far. We're going to test these rational zeros. Well, we're not going to necessarily test them, but we're going to use these rational zeros in the synthetic division process. First of all, I'm going to divide x minus 1 into f of x. F of x has coefficients of 3, negative 22, 55, negative 46, and 10. I bring down the 3. I get negative 19 here. And then 55 minus 19, I next get 36, negative 10, and a remainder of 0. So x equals 1, we had already determined was a rational 0, but now we can also factor f of x into x minus 1 times 3 times x cubed minus 19x squared plus 36x minus 10. Let's move on and use synthetic division with our rational 0 of 1/3. Notice that we're now looking at this polynomial factor, and we're going to divide that polynomial factor by x minus 1/3. So we'll put 1/3 in brackets here. We bring down the 3. We have negative 18. We have 30. And we get a remainder of 0. So we further have factored f of x into x minus 1 times x minus 1/3 times 3x squared minus 18x plus 30. Before moving on, I'm going to factor out a 3 so that we have x minus 1 times x minus 1/3 times 3 times x squared minus 6x plus 10. Now we cannot factor x squared minus 6x plus 10 over the real numbers, so let's move on to another slide where we will use what we found so far, and I will apply the quadratic formula to find additional zeros. So right now we've factored f of x, and we found that we have two rational zeros of 1 1/3. The next step then would be to look at x squared minus 6x plus 10. I'm going to set this polynomial factor equal to 0. Then we'll use the quadratic formula. We have x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. We simplify to get 6 plus or minus square root of negative 4 over 2, or 6 plus or minus square root of 4i over 2. And that is the same as 6 plus or minus 2i over 2. And then finally, we will see that we have zeros of x equals 3 plus I and 3 minus I. Okay, so altogether we have 1, 2, 3, 4 zeros here, 2 real, 2 not real. And now we're moving on to the try on your own for this part of the lesson. This is try on your own number 2. Find all zeros of the polynomial and factor to linear and irreducible quadratic factors. F of x equals x cubed plus 2x squared plus x plus 2.